In the second half of section 2.1, we will learn about some special sets. Now, keep in mind, as we progress through chapter 2, there's going to be lots of notation and lots of new, possibly unfamiliar symbols. It's a good idea to keep a list of these symbols and this notation so that you can master it as we go and you don't feel too overwhelmed. Definition. The empty set, our first special set that we're learning about, also known as the null set, is a set that contains no elements. That is, it is empty. There's two ways that we can denote the empty set. One way is with a set of curly braces that contains no elements, or a zero with a slash through it. What zero does for real numbers, the empty set does for set theory. It's sort of the idea of zero for sets. In example 5, we want to determine if the following sets represent the empty set. Example A, we have the curly braces, which indicate that we are dealing with a set, and we see the element 0 in that set. This one is not the empty set because it contains an element. That element happens to be 0, but the set itself is not empty. Example B, we have the number 0. The number 0 is an element of a set. There's no curly braces, so we're not dealing with a set. Therefore, this is not the empty set. Let's look at example C. Now remember, in the previous lecture video, we looked at two types of notation. We looked at roster notation and set builder notation. Notice example C is written in set builder notation. We read it, the set of all x such that x is a number greater than 10 and less than 4. Now, in this chapter and the next, we're going to spend a lot of time learning the difference between and or. Those two words seem to be interchangeable in English, but they're very specific in math. So let's examine how it affects these next two problems. We're dealing with a number strictly greater than 10 and less than 4 at the same time. Can you think of a number that is both bigger than 10 and less than 4 simultaneously? No, it's not possible. So this set, given in set builder notation, is an example of the empty set. That is, there are no elements that belong to this set. Example D, the set of all x such that x is a number greater than 10 or less than 4. So in this case, we're looking for a number that is either bigger than 10 or less than 4. Notice the word or completely changes the elements of the set. The elements of the set have to either be bigger than 10 or less than 4, but not exhibiting both properties simultaneously. So we can think of numbers that are either greater than 10 or less than 4. So this is not the empty set because it contains elements. Another example of a set given in set builder notation is example E. We read the set of all x such that x is a square with exactly 3 sides. Now, we know that the definition of a square is a polygon with 4 equal sides and 4 right angles. It is not possible that a square has exactly 3 sides. Therefore, we are dealing with the empty set. You may have solved an equation in a math class before and figured out that there was no solution for that equation. In that case, we would say the solution set is the empty set. The last example here, example F, is a little bit tricky. Notice we have the curly braces, so we are dealing with a set, and there is an element in those curly braces, but the element in there is the symbol for the empty set. This is not the empty set. Remember, there are two ways to denote the empty set. Either a set of curly braces with no elements or the 0 with the slash through it. Don't get overzealous and use both types of notation, or you will end up with a set containing something which is not empty at all. So our first special set is the empty set. This again is building a foundation for what we will be doing in the rest of Chapter 2 and also in Chapter 3. So at this point we can say we understand that an empty set has special notation. It is a set with no elements. Another set that you want to be familiar with the symbol is the set of natural numbers. Our next definition, the set of all natural. The next set that you'll want to be familiar with the special symbol is called. Another set that you'll need to be familiar with the special symbol is the set of all natural numbers. Natural numbers are our basic counting numbers. These are numbers 1, 2, 3, 4, etc. The special notation for the set of all natural numbers looks like this. It's an N with sort of a double bar along the diagonal. If I'm going to write it by hand, I'm going to write the N and then put an extra diagonal in that letter. In roster notation, we could say this set of natural numbers is equal to the elements 1, 2, 3, 4. The ellipsis indicates that we are dealing with an infinite set. So the roster notation simply establishes the pattern for the first few elements of that set. The natural numbers were very likely the very first numbers that you ever learned. When you learned about numbers, you learned how to count starting with 1, 2, 3, 4. The natural numbers are actually a smaller category within the set of real numbers. The set of all numbers on a number line are called real numbers, and they have a special notation as well. It's the R with the double bar on the left. You may have seen that in an algebra class before. Real numbers can be subdivided into different categories. Real numbers represent every possible location on a real number line. So if we look at a number line here, we can start by placing our counting numbers. Our counting numbers are the natural numbers. So the natural numbers are represented by the N with the double bar on the left. And again, these contain values like 1, 2, 3, continuing. That is an infinite set because we can continue counting and adding 1 indefinitely. Now, if I add a single value to that set, 0, we end up with the set of whole numbers. Whole numbers have a special symbol as well. It's the W with the double bar on the left. This contains the elements 0 plus all of the counting numbers. It is also an infinite set, but it has one more element than the set of natural numbers. Now, if we take the set of natural numbers and we reflect them over here to the other side of 0, we end up with integers. Integers are positive numbers, negative numbers, and 0. They have a special symbol which looks like a Z with the double bar. We can denote this with two ellipses, one on the left to indicate that the integers extend to negative infinity. We'll establish a pattern here, -3, -2, -1, 0, 1, 2, 3, and an ellipsis on this side to show that they continue increasing indefinitely as well. Now, if we look in between those integers, for example, at the number 1/2, we end up with a set of rational numbers. Rational numbers have a symbol which looks like a Q with a double bar at the left. Remember, Q for quotient. This is the set of all numbers such that the number can be expressed as a fraction. So that includes numbers like 1/2 or -0.6, a terminating decimal, or even a repeating decimal like 0.333 repeating, for example. The very last type of numbers that we can locate on the real number line are irrational numbers. The symbol for irrational numbers is an I with a double bar. This is the set of all x such that x cannot be expressed as a fraction. Okay, so again, examples of rational numbers or numbers that can be expressed as a fraction might be 1/2, -0.6, or 0.3 repeating, whereas an example of an irrational number might be something like pi or square root of 2, something like that. The most important sets that you'll need to know about are the natural numbers. We're going to use those most often in this set, but it is also good to be familiar with the other subcategories of real numbers. But again, our focus is the natural numbers. So to glean from this section the most important details, make sure that you know how to denote an empty set and how to denote the set of natural numbers.